Well, I wanted to take the time after class to go through a few more examples from electron configurations out of chapter 6. So here we're looking at a 10 atom. Something I like to make sure that I do when I'm doing a configuration is kind of check to see where the atom is in the periodic table. It happens to be in the row of carbon. Now the reason why I might do this is if I notice carbon's a 1s2, 2s2, 2p2, that we share the same number of valence electrons. That if carbon has 4 valence electrons, and so too should tin. So tin should have 4 valence electrons without even really doing the problem. Like if you look at fluorine, fluorine has 7. Iodine should have 7. So that's one consequence is if you know the row the atom's in, the valence count should match up. And we should be able to show this for sure in a minute. But our configuration for tin, it's through krypton. So we've kind of capped off our configuration through krypton. So we have the krypton configuration, and then if you forget, is it 6s2? Is it 4s2? We'll just count down. Hydrogen's 1s2, lithium's 2s2, sodium 3s2, potassium 4s2. Then we're filling into the rubidium row, so this is going to be a 5s2. And then we've already filled a 3d block within the krypton configuration, so now we're filling into the 4d. So we go all the way across the 4d for 10 electrons, and then we finally fill back into the 5p. Now, if you're wondering how do I know it's 5 and not some other number for p, we'll just go to the boron groups 2p, aluminum 3p, the gallium group 4p, and then the tin group would be 5p. And so the 5 for the p and the 5 for the s are the same number as well. And so this is our configuration. We can double check. Krypton's 36 electrons plus 2 plus 10 plus 2 is 50. And we should have 50 electrons for 10. So 10 is element number 50. So that matches up. That's good. And then in terms of our valence electron diagram, well, we only have really these two as our valence orbitals. So I have something like this for my 5s and my 5p. I get 3 5p orbitals. That's why I have 3 lines here. 1 5s orbital. That's why there's 1 here. Sometimes you might see the 4d written here. And here we just have our 5 and then 10 electrons. So we have our 4d subshell, it's 5 across, and then it's completely spin paired. So you could probably leave this off because, again, it's really not a valence orbital, so why would you include it in the valence electron diagram? But sometimes you'll see it shown. And so then our outermost or our highest n value is our highest shell. So that's these 4 electrons. So that's our valence electrons. The 4d is a lower n value and it's filled. So we don't count the 4d10. So these 10 don't count towards the valence. They're still there, but they just don't count towards the valence. And then our unpaired count, or how many electrons that don't have their spins paired up, that's these 2 electrons here. So we have 2 unpaired electrons. This question here is one that's good to ask because it makes sure that we have the right configuration. We're putting our electrons in correctly. And so as you go from 1s, 2s, 2p, 3s, 3p, then we saw 4s, then 4d, how do you know where to go from 4p? It's like, we'll just follow the periodic table. The periodic table then goes 5s, then it goes to the 4d, then it goes back to the 5p, then we come to the 6s, and then there's a little bit of a question, but it's really the 4f, and we'll see that we're filling in our, like once we go from cesium and barium, we then go lanthanum across to whatever the last one is there. So we fill in the F block generally next. Then we go to the 5D subshell. We already filled the 4D, so we go 5D. This would be across to mercury. Then we go back to the 6P, 7S, 5F, 6D, and then the 7p, and this is our periodic table. So, I mean, this is as far as we're going. And even some of these last elements only exist for a very small fraction of a second through some really high energy nuclear reactions that form them. Okay, so coming back to our diagram here, this is just kind of showing what we just showed before. I go 4s, 3d, 4p, 5s, 4d, 5p, and then 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. So you're just literally just going in order left to right here. And you can construct this. This is just literally putting the 4f and 5f subshells back into the periodic table, and your periodic table that you'll see like with exams, has this f block shown down here. So let's consider lanthanum. Lanthanum is a peculiar element for a couple of reasons, but lanthanum, we look at the configuration. It's element number 57. Should be the first in the first element to use an F subshell. So it comes after barium, and barium precedes the noble gas as xenon. So xenon has 54 electrons. Lanthanum should have 57 electrons. So then we go 6s2. Now, how do I know it's a 6? We'll just count out. Hydrogen 1, lithium 2, sodium 3, potassium 4, rubidium 5, cesium 6. 6s2. And then 4f1 is what we expect. So this is our expected configuration here. But then it turns out that it has one of these anomalous configurations. That it's really a xenon 6s2 5d1. So an anomalous configuration is one where we just have some other configuration that turns out to be more stable than the one we expect. Now, this is why if you look in our classroom, our periodic table has lanthanum up in the D block, or it looks like it's in the D block. It's because it kind of is. And then after this, we then start filling into the F subshell. So if we go to the next element, I believe is cerium. So cerium, we should expect to be fall back in line. So we go back to what we expect, 6s2, and then a 4f2. And so you'll see the F block is either, a 4f, however many you expect, or maybe it moves one or more electrons into that D subshell. And it just turns out sometimes moving electrons around relatively similar energy subshells is possible. So you get some interesting configurations. We'll look at a few in a minute. But our valence electron diagram here for either of these, like you can come up with it, it's basically the same diagram. You have two spin paired electrons, and you have either 1, 2, 3, 4, 5, 6, 7 for your F, and just with one of them using the electron. Or you go ahead and just draw 5 and picture it being a 5D for the anomalous configuration. You still get one unpaired electron for each. So no matter which of these configurations you're looking at, for 6s2 5d1 or 6s2 4f1, you would get 3 valence electrons and then 1 unpaired electron. So the questions we usually ask, you usually don't need to know if it's anomalous or not. And we really don't want you memorizing the elements that are anomalous because it really is kind of random. Let's look at a bigger element now, tungsten. Tungsten is in the D block. It's in the third D block, so it'd be 3D, 4D, 5D. So this should end in a 5D configuration. So tungsten, 74 electrons. The nearest preceding noble gas would still be xenon. So that's 54 electrons. 6s2 like before. We float all the way across the 4f14. Now, how do I know 4f and 14? Well, 4f is what comes next. And then why 14? Well, there's -3, -2, -1, 0, 1, 2, and 3. So there's 7, 1, 2, 3, 4, 5, 6, 7 f orbitals. 7 4f orbitals. So 7 times 2 is 14. And then our last few electrons. So tungsten has 4 electrons, or excuse me, tungsten's element number 74. So it's the 4th element across the D block. So this would be a 5d4. And if we double check our count, 56 plus 14 is 70 plus 4, 74. So we've distributed the proper number of electrons. Our valence electron diagram would look like our 6s2, spin paired electrons, 1, 2, 3, 4, 5. We don't we don't predict an anomaly. Like we don't look and say, well, chromium is in the same group as tungsten, so it might do the same anomaly. We don't predict that. We just say we expect this one. Don't worry about if it has one of these anomalous configurations. So this would be our 6s2 5d4. So 4 electrons into the 5d orbitals. One's empty. And then we could show the F, but again, this is kind of unnecessary. 2, 4, 6, 8, 10, 12, 14. I would have been better off to go 7 across and then spin pair across. but whatever, you get 14 in the F block, all spin paired. So we have 2 plus 4 valence electrons, we have 6 valence electrons, and then we have 4 unpaired electrons. 4 unpaired electrons. And then lastly, for an example here, lead's back underneath tin, so we should know the count is 4 just from carbon's 4, tin's 4, lead should be 4 valence electrons. So lead would still be a xenon, 6s2, 4f14, build all the way across that 5d subshell, then we come back to the 6p2. So we have 4 valence electrons from our valence diagram, 2, 4, and so we have 2 unpaired electrons. Okay, so this here is the periodic table for the basically the first transition metal row and below. So the fourth row of the periodic table and below. And if you notice that the configurations, and if we had shown these configurations, they're exactly as we expect. So there's no like anomalies. There's no configurations in the 2p through 3p subshells that were different than what we expect. But if you notice, let me zoom in a little bit more, that you see that chromium is different than you expect. We expected 4s2 3d4, we get 4s1 3d5, and then we get an anomaly at copper in the first row. If you then notice in the second row, I'm just going to underline the anomalies. We get molybdenum is anomalous, ruthenium and rhenium are anomalous, palladium and silver. We actually have 4 anomalies in the next row of the periodic table. And then if we look at the third D block, we see that tungsten is exactly as we expected. It didn't actually follow suit with chromium and molybdenum. And then if we notice that ruthenium and rhenium wasn't really periodic because we get exactly what we expect for osmium and iridium. Platinum has an anomaly, but notice it's a weird anomaly. It's not even the same as palladium's. And then gold is anomalous. So it's very peculiar. Notice that you have 2 of 3 like chromium, but the third doesn't do the anomaly. Then notice that you have copper or nickel is exactly as expected. Palladium does one anomaly. Platinum does a different anomaly. So notice that they're both anomalous. They're both different than what you expect, but they're not even the same type of anomaly. And then copper, silver, gold all do the same anomaly. So it's very peculiar to understand or to predict when these anomalies occur. But the issue is just some configurations are more stable than others, and some subshells are closer together in energy. So sometimes a slight difference in configuration stability counters the slight difference of orbital energies being higher for like the D subshell versus the S subshell. And so just know that sometimes anomalies occur. You don't have to predict when they occur, but there's just sometimes the configuration is different than what we expect. We're not losing electrons, we're just moving them from one subshell to another. And another place this happens is lanthanum, we mentioned earlier, was different. Cerium actually is a 4f1, 5d1. So it should have been a 4f2 based on our rules, but it ends up being a 4f1, 5d1. Then if you go to praseodymium, you may think, well, is it a 5D1, 4F2? And the answer is no. For some reason, it's a 4F3, then 4, 5, 6, 7. Then we kind of go back to having some goofy business with gadolinium and some of these other elements from there. Actually, I guess after gadolinium, they're all as we expect. And then in the final F block, we see some D's where they should be F's. So we see some anomalies here as well. So a few anomalies in the lanthanide and actinide series. But again, don't worry about predicting when the anomaly occurs. Just know if we give you a configuration that's anomalous, you can still tell us what element it is. Like if we tell you some element has, a 6s1, 4f14, 5d1 configuration, well, we should be able to work out that that's gold just by adding these electrons up. So 15 plus 10 is 25 electrons on top of xenon. So 25 plus 54 should be element number 79. Element number 79 is gold. So just add up the electrons if you're given a configuration. Then the last question from the notes was chromium has one of these anomalies that we showed. It's really a 4s1 3d5. How many total unpaired and valence electrons does the atom have? Well, we said in class, well, we expected a 4s2 3d4. And if this were the case, we would have had 4s2 and then the 3d 1, 2, 3, 4, 5. We would have had 4 electrons unpaired. 6 valence. And then the actual configuration, or the anomalous configuration, anomalous just means the true actual configuration is a 4s1 3d5. So notice we just took 1 electron here and put it over here. And so that just gives us 2 extra unpaired electrons. So we spin pair all of these electrons. So we have 6 unpaired electrons in the true configuration of chromium, not 4 that we expected. So 4 turned out to be wrong for chromium. Okay, so I just wanted to take the time to go over a few more examples from where we were at in class today so that we can spend all of next week working on review topics for chapter 6. And that way you guys have now seen basically all the examples I plan to go through from chapter 6 before hitting review problems so that you can begin studying for the exam if you want to over fall break. So enjoy the break. It's also a bye week, which works out well for us having a test next week. So have a great weekend and have a great break. See you on Monday.